Hi everyone, I'm Anika and welcome back to 8th grade science with Alston. This video covers the Earth History Standard. It's about the ages of rocks and evidence of Earth's history. As always, all of our questions are time-stamped, so you can skip past the explanations of questions you get right. If you need extra review on specific topics after this video, go to our links for further reference page. This page has a link that goes with each question in the video, so you can work on the challenging ones. This page is linked in the description box. Alright, let's get into the first question.
Question 1. Based on the law of superposition, which of the rock layers in the following diagram is the oldest? The answer is C. The law of superposition states that each rock layer is older than the one above it, assuming that the layers have not been disturbed after they were deposited. This is because each rock layer is deposited on top of the ones that were already there. This is a form of relative dating because it only helps scientists find a rock layer's relative age, not its exact one. A rock's relative age is how old it is compared to other rocks, not its age in years. If one rock is younger than another, that's a relative age. If a rock is exactly 95 million years old, that's its exact age. By these, we know that C is the oldest because A and B are above it. This means that A and B must have been deposited after C. Question 2. Which of the following is not a characteristic of index fossils? A. Must only have existed for a short specific time in Earth's history. B. Must be unique. C. The fossils of the organism must be common. D. Must be a large fossil. Or E. Must be found over a widespread area. The answer is D. Must be a large fossil. Index fossils are fossils that are used for relative dating. The most important characteristic of an index fossil is that it only existed on Earth for a short period of geological time. If scientists know the period during which an index fossil lived, they can also know the age of a rock layer that the index fossil is in. Let's take an example. In this diagram, these circles, the yellow circles, represent an index fossil. We know that it is an index fossil because this organism existed on Earth for only 3 million years, which is very short when considering that Earth is billions of years old. This organism existed 2.5 billion years ago. If rock layer C has the index fossils, this must mean that rock layer C is 2.5 billion years old. But why must the index fossils only have existed for a short period of time? Let's look at the red triangles. These are normal fossils, not index ones. Let's say the triangle fossils have existed for 1.2 billion years. Because we know that rock layer C is 2.5 billion years old, thanks to the circle fossils, we know that the triangle organism existed anywhere within 1.2 billion years after that. If scientists look at rock layers A, B, and C, they won't be able to narrow down their ages to a specific time period using the triangle fossils. The triangle fossils only show that these rock layers were formed somewhere in that 1.2 billion year time period. That's not specific enough, even for a relative age. Some other features of index fossils include must be unique because index fossils must be easily recognizable and different from other organisms, must be common because if there was just one single circle fossil in rock layer C, that wouldn't be enough evidence to say that rock layer C is 2.5 billion years old. What if that single fossil had been displaced from another rock layer? However, index fossils must not be in too many rock layers. If the circle fossils were in all three layers, like the triangles, they would have had to have existed for much longer than 3 million years, and then they wouldn't be index fossils. Index fossils must also be widespread because of the other use of them, matching up rock layers that are very far away from each other. If rock layer C has the circle fossils and another rock layer that's very, very far away from it has those same fossils, this means that both rock layer C and the other rock layer are approximately the same age, 2.5 billion years old. Based on these known characteristics of index fossils, we can go back and narrow down our original multiple choice list. The only option here that's not required for index fossils is D, must be a large fossil. There is no requirement for the size of an index fossil. As long as it's unique and scientists can recognize that it is different from other organisms, it can be any size. Question 3. Based on the principle of cross-cutting relationships, which of the rocks in the following diagram is the youngest? The answer is D. The principle of cross-cutting relationships states that any type of fault or intrusion in a group of rock layers must be younger than all the rock layers it cuts through. Things have to exist before something else can cut through them. A fault is a break or crack in rocks. An intrusion is when molten rock forces its way into the layers of sedimentary rock above it, then cools to form igneous rock. Based on this principle, we can see that rock D is an intrusion. It cuts through all three of the other layers, A, B, and C, meaning that A, B, and C must have existed before the molten rock that formed rock D pushed its way through them. This means that D must be the youngest. Question 4. What is the most common type of rock on Earth's surface? The answer is sedimentary. Sedimentary rocks are the most common type of rock on Earth's surface. Scientists often study layers of sedimentary rock to learn about Earth's history. It is important to note that sedimentary rocks are the most common on the surface, not in the crust. That would be igneous. Question 5. Which of the following is the main reason why ice cores are important to understand Earth's geologic history? A. They help scientists understand the past climates of Earth. B. They help scientists understand how ice formation has changed over the years. C. They help scientists understand now extinct aquatic organisms. Or D. They help scientists understand plate tectonics. The answer is A. They help scientists understand the past climates of Earth. Ice cores are samples taken out of ice sheets or glaciers that were formed from years and years of snow. Eventually, the pressure on this snow is so high it becomes glacial ice. So, what's the importance of these samples? When snow falls, it brings with it all the particles that are in the atmosphere. Over time, as this snow is pressured into becoming ice, those particles are trapped in the ice too. Gases from the atmosphere at that time are also trapped in little pockets in the ice. When scientists extract and study these ice cores later on, they can see the different layers of different years of snowfall because each layer has a different composition of particles and trapped gases. Then they can identify how old each layer is and see what particles were in the atmosphere at that time and also what gases and how much of them were in the atmosphere at that time. Using ice cores, scientists can put together the composition of the atmosphere at different times in history. This is important for two reasons. A. Certain particles can be evidence of significant events in Earth's history. For example, if there is volcanic ash in a 750,000-year-old layer of an ice core, this must mean that there was a volcanic eruption in that area at that time. B. Knowing what gases were in the atmosphere at different periods of Earth's history can help scientists track the trends in greenhouse gases and predict how our atmosphere will change in the future. They do input other variables too, not just the gases. By this explanation, we know that the answer is A. The other answers don't have much to do with Earth's past climates or atmosphere. We would have immediately been able to eliminate choices C and D. Choice B seems very possible, but the exact process of ice formation doesn't really change. Snow falls on top of snow over and over. Eventually, the pressure is great enough to make ice. Question 6. Fill in the chart using the following word bank: mold fossil, cast fossil, trace fossil, petrified fossil, preserved fossil, and carbonized fossil. Go ahead and pause the video here so you can look at the table and pictures for longer. So here's the full table. The first was trace fossil, second petrified fossil, third carbonized fossil, fourth mold fossil, fifth cast fossil, and sixth preserved fossil. Fossils are different because they were formed in different ways. You should know the basic processes of formation of these 6 types of fossils. Question 7. What method do geologists commonly use to find the absolute ages of rocks? A. Law of superposition. B. Radiometric dating. C. Index fossils. D. They compare them to other similar rocks. The answer is B. Radiometric dating. Based on earlier questions, we know that the law of superposition and using index fossils are both methods of relative dating. This is because both of them only give an approximate range of how old the rocks could be, not the exact age. The same goes for comparing them to similar rocks. While similar rocks could have the same age range, A, that's not always true, and B, that's still not an absolute range. What geologists do to find absolute age is measure the amount of radioactive materials in a rock sample. Radioactive parent materials decay to produce non radioactive daughter materials. By finding the amount of time it takes the radioactive material to decay and comparing the amount of parent material and daughter material, they are able to find the absolute age of the rock. This method is called radiometric dating. Question 8. What is the geologic timescale? A. A record of all the major events and diversity of life forms present in Earth's history. B. A record of all the different landforms on Earth over time. C. A timeline of all major geological discoveries. D. A timeline of Earth's formation, starting from the Big Bang. The answer is A. A record of the major events and diversity of life forms present in Earth's history. The geologic timescale starts when the Earth was formed and goes on till present day. It is split up into different lengths of time. The ones you need to know are the eras. The end of the eras are marked by mass extinctions. There are 4 eras on the scale, each known for different life forms. Last question. Question 9. Match the 4 eras to their description: Precambrian, Paleozoic, Mesozoic, and Cenozoic. Go ahead and pause the video here so you can get more time to look at the table. This is the full table. The first was Paleozoic, second Mesozoic, third Precambrian, and fourth Cenozoic. These aren't in the actual geological order of the eras. I'm just saying the first answer was Paleozoic, second Mesozoic. What's really important to know from this table is that the Cenozoic era is the current era, and that the Mesozoic era was when dinosaurs existed.
If these questions were helpful for you, please like, share, and subscribe. Check out our links for further reference page for any further review. Thanks, and I hope to see you in the next video.